Thank you very much. Thank you for the organizers first to give me this opportunity to present this work. So this is a recent work that is submitted. It should be published in not too long time. And here is the work is focused on the impact of accretion on the cosmic dust growth. Okay. So why cosmic dust? First, because it's ubiquitous in space. We found it in ISM, around supernovae, near stars. And the dust divides generally in two main types. So one type is around oxygen-rich stars. And in the surrounding, because the oxygen is much more present than carbon, the C/O ratio is lower than 1. And in this case, all the carbon is basically trapped into CO. And the dust that is formed in those regions is a silicate type of dust, which is relatively complex, contains silicon, but also magnesium, aluminum, iron, oxygen, and calcium. And there are many different types of those dust depending on the seed, with different proportion of those elements. So those dust are usually a bit complicated to model. And there's a simpler type, which is around carbon-rich stars, because those around those stars, the C/O ratio is higher than 1. So all the oxygen is trapped into CO. So we have in this case a carbonaceous type of dust, which is simpler in structure. It can be amorphous carbon or amorphous-like or graphite-like type of dust. So why dust is so important, in addition of the fact that it's ubiquitous, is because the dust is very useful in shielding molecules from being destructed by radiation. So the molecules that can be trapped on the dust cannot be destroyed as easily. And also because the molecules present can roam around the surface. And so the surface will act as a catalyst and will help forming complex molecules like amino acids or nucleobases. And so this dust is very important because it's the reason why the chemistry in space is so complex and can form such large molecules. For example, glycine that can form on ice has a barrierless path, which is not possible in gas phase. So this type of reaction can occur and form those complex molecules. So in this study, I focused on the carbonaceous type of dust, and in particular the amorphous carbon type, which is more frequent than the graphite-like seeds. So here the focus is on the dust formation and growth. And the dust forms in nucleation regions that are regions of in the winds of AGB stars, also in the ejecta of core collapse supernovae. And in this case, the temperature is relatively high, so from tens of Kelvin to thousands of Kelvin. Here I limited to a range of 50 to 2,500, because over this range anyway, all the dust is sublimated totally, and there is no dust present. And what is important here is that because the dust is forming, the dust is at the same temperature as the gas we can consider. So dust and gas will be same temperature, which is very different from the ISM condition. In the ISM, of course, the temperature of the dust can be very low, 3 Kelvin minimum, can be few hundred kelvins. But the gas, on the other hand, can be very high temperature because it can be excited by radiation. So we can have from 3 Kelvin to multiple thousands of Kelvin. So here we focus on the dust nucleation region because we want to study the formation and the growth of those dust seeds. One big difference also, contrarily to the dust that was presented earlier today, here we consider a case where the temperature is too high, so there is no icy mantle on these dusts, contrarily to the ISM conditions where there is some icy mantle that can form, which changes the structure or the surface of the dust where the accretion can occur. The modeling that we do is relatively simple. It's a model that includes accretion and desorption because growth comes mainly from those. I don't consider here the coagulation of two dust seeds that would coagulate together and form a larger seed. This is done by other people in the collaboration when I'm part of this project. And so here we consider just the accretion desorption of the main colliders in the nucleation regions. The accretion rate of any species I will depend on the surface of this dust, on the density of the species of interest, and of the thermal velocity of the gas. And of course, the important part that was also mentioned this morning is the importance of the sticking coefficient, which is a coefficient between 0 and 1, that will give an idea of how efficient is the sticking of any molecule that will collide. It's temperature dependent. It's also species dependent. And as was also mentioned this morning, in a lot of cases for modeling, the sticking coefficient is considered to be always 0.5 or always 1, regardless of the type of collider, but also regardless of the temperature. We consider also the thermal desorption. And here the simple Polanyi-Wigner formula that is a good model for thermal desorption. It depends on the number of surface atoms that we have on the dust, on the escape frequency. So this escape frequency is the vibration frequency of any bond between the atom that can eventually desorb and the dust. So this is the formula here, and it includes this exponential of minus E over kBT, E being the binding energy of the species of interest. And so those two values, the SI and the E, are relatively difficult and not so easily found in the literature. And this is what we focus on in this study. So here, as I said, we want to study the pure amorphous carbon type of dust, and we want common colliders sticking on it. And for common colliders, we focused on H, H2, CO, and CO. So the first part is to have an initial dust structure. I will explain just after what structure we take. It was something that was computed in a previous study. But we take multiple structures to increase the amount of different types of amorphous carbon structure that we use to have a better average value of sticking. What we want here is to thermalize the structure at the temperature of the dust. So we use a thermostat for that. And from this thermalized structure, we can actually compute the binding energy. In case of amorphous carbon, we can get the carbon binding energy to amorphous carbon by just taking the total energy of the structure divided by a number of carbon atoms. We can also do the same for C and O, also COH2, just by adding those atoms and looking at the value that is computed. So from this stage, we already have the knowledge of this binding energy that is useful for the thermal desorption. And on top of that, what we want is the sticking. So we have to add those colliders and make them hit the surface at thermal velocity following Maxwell-Boltzmann for the temperature of the gas. What is important here is to have enough colliders and to scan the whole parameter space. So basically all the possible angles, all the possible velocities following the Maxwell-Boltzmann to be sure that we have a value that is a good approximation of the sticking coefficient. And once this is done, from the binding energy, we can compute the thermal desorption. And from the initial structure that is collided by those partner collisions, we can obtain the sticking coefficient by looking at how many actually sticked compared to how many bounce back. And this gives us an accretion rate. And of course, from those, using the model that we decide to use in this study, we can obtain the carbonous dust growth modeling in those nucleation regions. So for the structure that we use here was the structure that was computed in 2018 in this paper by Volker Deringer et al. And they computed multiple structures of different size. So we took the largest one, which is 512 carbons. It has this die shape here. So it's not a square, of course, it's 3D. And this cube, we then thermalize it. And the thermostat we use is a Nose-Hoover chain. And those simulations, because it's many atoms, we have to use a reactive force field, which is relatively cheap in terms of numerical cost. And you can see here the structure at 50K. So the structure at 50K is relatively close to the structure that was generated by those people in the structure. To generate this, they actually used DFT calculations. They trained a neural network for this, and they generate those structures with close to DFT accuracy. So it's relatively accurate calculation. And something that's interesting here is that when we thermalize this at different temperatures, we can see that the shape, of course, will change. And at very high temperature, some carbons are lost during the thermalization, but the remaining carbons are actually mainly forming 2D cyclic structure because the cyclic compound is so much resilient to temperature. And we can also see some carbon chains. And of course, this is reactive force field type of calculation is not very accurate, but I think it's already interesting to notice that the 2D cyclic compound in the carbon chain is something that we found a lot in space. And to see that naturally, just by thermalizing any amorphous structure, we actually obtain already those. So then we can imagine that PAH can easily be formed this way also, just by thermalizing structure. I mean, thermalizing in the media where the temperature is high, it will generate those type of structure. So as I said before, once the structure is thermalized, we can compute the binding energy. So it's also based on this force field calculation. And here is the value we got for H, C, and O. For H and O, I didn't find any comparison in the literature, but for the carbon, there was some data available on graphites, and it was actually slightly higher, which is expected because in graphites, you expect the carbon to be more bonded. So this is something that we were relatively confident in the values that we obtain. So we have to keep in mind that those values are probably slightly overestimated because this is the value of the whole amorphous carbon structure. But you expect that during desorption, the carbon that are less bounded will leave first, which means the one that have a binding energy that is a bit lower. So we know that this is slightly overestimating the actual physics. So now that we have this structure that is thermalized, we want to do the dynamics. And so for this, we use this reactive force field, which allow creating or breaking bonds. And we decide to launch 74 incident atoms per structure. As I said, we use 10 structure to have more statistics, and per species. So here is just an example to show you how it looks for oxygen in red heating the amorphous carbon at 250 K. And we can see that in some case, of course, they just bounce back immediately. In some case, they immediately create a bond. But in other case, we can see the oxygen atom roaming around for a while. I don't know if we'll see some of it. Voilà, this one, for example, is physisorb for a while. This one also is physisorb. So there are two types of reaction we can get. We can get chemisorption or physisorption. The thing that we consider growth to be only possible through chemisorption, because physisorption is not really bounded. It's just van der Waals, so it can be easily pushed away. And for the H2 and CO, we actually only saw physisorption, which makes sense because it's a saturated valence, so we expect no bond creation. And it's also a very strong bond. I think H2, the bond is like 48 or 49,000 Kelvin. And the CO being the strongest bond is over 100,000 Kelvin. So for a simulation up to 2,000 Kelvin, we don't expect the CO bond to be broken, for example. So this was not so surprising. But for the case of H, C, and O was different. We had both physisorption and chemisorption. So the idea here is to say, okay, chemisorption is useful for the growth. Physisorption is not. What do we do with those physisorbed atoms? Do we expect that they all leave the surface? Do we expect that they all stick at some point? So what I did here was to extend the calculation to longer time and look at the proportion of physisorbed atom that would, in the end, or chemisorb or desorb. So this is the little plot that is here. You can see that for H, the probability that a physisorb atom finally chemisorb is very high, it's close to 1. There is no point over here because there was no physisorption anymore. For carbon and oxygen, the probability is relatively high, but it decreases fast. So over 150 Kelvin, most of the physisorb atom will just desorb at some point. So we use this probability to compute an estimated chemisorption, which is basically an asymptotic value of a long time. So this was possible because we saw that the average collision time in the type of density we have in nucleation regions is over the second, it's larger than the second, but the typical time for physisorption to either be chemisorbed or desorbed is much lower. It's probably about microsecond at maximum. So we can easily say that every physisorb atom will have time to either desorb or chemisorb before the next collision arrives, so they don't interact. So we could do this approximation and say, we will take this probability and multiply all the physisorb atom by this to obtain an estimated chemisorption. So this is the result obtained for H, C, and O. So as you can see, there's physisorption in yellow. In some case, for hydrogen, it's almost 0. And in some cases, very high at low temperature. But using this probability, we could convert those physisorb atom into asymptotic chemisorption. And this is actually very important because if you miss this part, you actually obtain a chemisorption that goes close to 0. If you include it, you can see that the sticking coefficient actually increasing at low temperatures. So typically in some experiments, it means the time over which the experiment is done can change the value of sticking you obtain. And this asymptotic value is giving an infinite time estimate. Then the profile is also something important to notice. The profiles are very different. So using the same sticking coefficient for those 3 atoms would be wrong. In some case, they're relatively constant. In some case, they are very low. So this has to be taken into account. So now that we have the values of sticking coefficients and the values of desorption, we can use this in modeling of dust, as explained at the beginning. And we can equalize the desorption and the accretion rates. And when those two are equal, we can consider this is the sublimation temperature, because over this temperature, the desorption will be more efficient, and below the accretion will be more efficient. So something important here is that the sublimation temperature of carbon is much higher than sublimation temperature of hydrogen, which means if you consider the dust that forms at high temperature will be pure amorphous carbon before the hydrogen is able to stick. So starting from pure amorphous carbon actually makes sense. The other type of result we got was this effective accretion, which was a balance between accretion and desorption. And we can see here that, of course, over sublimation, it drops to 0. It's relatively flat here. It's flat because the amount of the density of each atom is reducing when they accrete on the dust. So even if the rate, if the rate here is increasing, the fact that the amount of carbon available is decreasing, it makes this almost flat behavior over time. And from this data, we can get the dust composition in terms of carbon, hydrogen. In this case, there are only those 3 atoms and oxygen, but oxygen is trapped into CO. And we can also obtain the dust size for any chosen temperature in those nucleation regions. So these were the main results of this work. So for the future direction, first, we only consider 3 atoms. So the goal is to increase this to more atoms that are present, the main colliders of those regions. And the second thing is to extend this to ISM conditions. So temperature of dust being decoupled from temperature of gas and going from 3 to 300, and for the gas go up to 10,000. So for this, of course, because the sticking coefficient is relatively smooth in terms of behavior, it's a good way to use machine learning. So this is an ongoing work. I used a multi-layer perceptron, which is a basic neural network to try to do just ND interpolation. And we can see here that for very few data points in purple for H, for example, we can interpolate those and create this surface. But the learning here is not done only on H, it's done also on H, C, and O, and the behavior of each one is helping the other. So the goal, the long-term goal, is to extend this to more atoms and to be able to basically share this neural network, these codes, so that in the future you could put any atom you want for any temperature of gas and dust, and the prediction will give you immediately the value of the sticky coefficient to be used in any astrophysical modeling. So for this, I acknowledge the collaborators of this work. So Gunnar Niemann, that is in University of Gothenburg, and Arka Sarangi, who is doing the dust modeling for this work. And this was part of the Wallenberg Foundation funding for the origin of fate of dust in the universe. And I thank you for your attention. I hope I was not too long.